Hi everyone. So this is a video about our project for the class Big Data Analytics. We did a analytics project for the PokemonGo datasets. So just a brief on the motivation. PokemonGo is a mobile game that you can catch Pokemons, and it's very popular due to the real-time interaction. So what we did is that we used the data that was from the August this year that has about 300,000 different recordings of different kinds of Pokemons, where they appeared and what time they appeared, and what are the features such as the weather, the wind speed, and our goal is that we want to build a analytic tool so that we can predict, given the set of features, what kind of Pokemon it is like to appear. So as I said, the first data set we use is this data set from Kaggle that has about 300,000 rows and 208 columns. So it's pretty large. And what's more is that we also use a 311 data set. That's about the complaints updated on a daily basis that was received from all over the place in New York City. And we'll explain why we're using this data set. We also use some complementary data sets such as the types of Pokemon and their evolutions, and those will serve a nice purpose for our machine learning phase. So the tools we use include R, Python, PySpark for some machine learning, and systemg for various data visualization. We also use the machine learning library such as mlib and sklearn from Python and PySpark. Okay, so we're going to start with the exploratory data analysis. So first, because the table contains the co-occurrences of each two different type Pokemons, so we just did a adjacency table of 150 by 150, and each entry is how often these two types of Pokemons co-occur together. And we build that network graph and we upload it to systemg. But the initial graph was just too dense to visualize. So this is the initial graph. And well, this is actually already filtered down to more than 100, but you can see it's still like very dense. So we decided to do some further filtering, and we specified that we only show edges when two Pokemons have more than 500 times that they co-occur. And now the graph becomes much easier to read. You can see this is different kinds of Pokemons, and the color of the node is about their type. So you see that roughly some same type have some co-occurrences, but it's not exactly very clear what is the network structure. But that kind of makes sense because in the real world, different types of Pokemon can also occur like close to each other in the same location at around the same time. Also, the nice feature about systemg is that you can focus to query only on one Pokemon. So here we zoom in onto the Dragonite, and as you may know, that's a very rare Pokemon. So not surprisingly, Dragonite has connections with lots of other type of Pokemons. That's probably because whenever Dragonite appears, that's such a rare event, so that you have to wait and you see lots of the other kind of Pokemons before you see a Dragonite. And then once Dragonite is gone, you see those Pokemons again. Also, we plotted the physical location of those Pokemons all over the world. So you can see that they are in all Europe and most of North America, some Australia, some Asia, and some South America. Intuitively, it seems that water type Pokemon should be nearby water. So we filter to see where those water type Pokemon appear. But it's not very clear from the graph that they're nearby water. And that's probably because the map is so global. So we really need to zoom in to see the local water regions. So that was some initial data in visualization. And then we want to look at the modeling part. So we first use two non-parametric models to predict the labels of a given Pokemon. The first one we use is k nearest neighbor. So here we use two different metrics. The first one is L1, the second is L2, or the Euclidean distance. And there are actually two graphs here, but they are so close to each other, so it almost appears that there's just one graph or one line. So you can see that, not surprisingly, the task accuracy gets lower and lower as we increase the number of neighbors. So it indicates that it's best just to use the closest one or two neighbors to achieve the best test accuracy to predict whether this Pokemon is a water type Pokemon or not. And the next one we use is called random forest classifier, which is a classic ensemble learning method. So there are two parameters we're tuning here. The first one is the number of trees, indicated by the different curves here. And the second is the max depth that each tree can go down to, and that's what we have on the x-axis. So not surprisingly, as we increase the depths, the training accuracy gets higher and higher. And also, the top curve is the one with the most number of trees. So that's everything that theory tells us. And now when we apply these models to the test data sets, we see that there is novice overfitting. As you can tell that once we pass the 15 level thresholds, the test accuracy just goes down. So it seems that 15 layer is the best one to use for whatever number of trees we have. Now it's time for testing some of the parametric models. So the first one we use is logistic regression. It's a linear classifier. And for the purpose of this video, we also want to show what we did using PySpark for building this predictive model. So essentially, first thing we did is that we exported the data into a CSV, and it has a label, which is the first data point here. So in this case, this is 0, meaning that the row is not a water type Pokemon. And then these two numbers are the latitude and the longitude, and all those flow numbers are different things. You see a lot of zeros because we have lots of dummy variables here. So we use a map function, which is a transformation. We actually use 3. 1, 2, 3. Then we need to transform the data again into something called parse data, which is data structure that is easy for PySpark to build a model based on. So here we simply just bisect data into the label and all the array containing the features. And also we did the 70-30 split between training data and test data. And finally, we did the accuracy. So it seems really interesting because notice that the training error is slightly above the test error, something usually that we will expect the opposite side of. But that's actually a good sign. That means our training error is that the model is pretty strong. Then we did a supported vector machine using the Gaussian kernel or RBF and also sigmoid kernels. So you see that as we increase the training sample size, the accuracy gets higher and higher, but then it gets lower and then higher again. So it seems that 2000 training sample is enough. And similarly for predicting whether it's a normal type or not and whether it's a water type or not. Okay, so everything so far is on a global scale, but what about on some local data? That's why we introduced the 311 complaint data sets. The first thing we did is that for different kinds of Pokemon, we're curious about in New York City, what is their daily frequency of appearances. You'll see that as they go up, nearby 5 a.m., that's where all three kinds of Pokemons, common, usual, and rare Pokemons, that's where every three type is at the peak. And then in the afternoon, it gets lower, everybody's working, and then in the evening, it gets higher again. And when you plot those occurrences in the map of Manhattan, you see some interesting patterns. Right? In the morning, it's some sporadic thing here on the Upper East Side. In the afternoon, it's very silent. In the evening, you see a lot of occurrences in the lower side of Manhattan. And then when it's night, when it's dark, you see lots of appearances of those rare Pokemons nearby Central Park. So we're curious if there's an association between the appearances of these rare Pokemons and the complaints that were received. So that's why we use the 311 data sets for the same week, by the way, for the first week of August. So first we filtered the complaint types down to these specific types because it doesn't make sense to say, whether a animal abuse or a highway drive sign damage was caused by some PokemonGo fans' crazy activity. That just doesn't make sense. So this is from 2015, and you see that for the same week, there's almost no activity of those complaints at all. There's one or two here, but it's really hard to see. So there's like almost none. And things change dramatically once you go to 2016, which is this year. You see some occurrences here in the morning from these same type of complaints. In the afternoon, it's almost like silent, as we saw in the very first graph, where no rare Pokemon appears. Then in the evening and the night, you see again those like activities or complaints occur, and in the night they are sort of around Central Park. They're not exactly in the Central Park, and our hypothesis is that the citizens in the Central Park, no one lives in Central Park, right? But there are like plenty of them living nearby the Central Park. So that's why they filed a complaint nearby the boundary of the Central Park. Okay, so the last slide was really a good example telling us that from the physical real data, we could import some of the knowledge and to build some richer features to enable us to tell a better story. In this predictive analytics project, we tried different machine learning methods, and it seems that k-nearest neighbors and logistic regression are the two best performing ones. The challenges we face are that the test accuracy isn't high enough, and that could be possible because the labels underlying distributions are not very distinct, since this is still, after all, a discriminative learning process. And also, some models still slow to train on large-size data, such as SVM, which has a quadratic time complexity. So next steps that we want to introduce some richer features, such as the physical features that we saw from the 311 dataset. The last few graphs obviously indicates that there is some interesting correlation between the complaint types filed and the rare Pokemon's appearances. And also, ultimately, we want to build an app to output the best location time to catch a specific Pokemon that the user inputs. And that's everything we have. Thank you so much.